So, hello everybody. It's our favorite program television show, Complex Differential Geometry. Um, so today we're going to be talking about the complex structure. Complex structure, uh, usually called J. But before we do so, let's recap what we've done so far in increasingly general terms. So in the first lecture, we went over topological manifolds. And I'd like to highlight kind of the how it relates to what we're going to do today. So we added something called CR differentiable structure. And this turned our topological manifold into a CR differentiable manifold. And if we set R equals to infinity, loosely speaking, then what we got was a smooth manifold. Right. So with a smooth manifold, kind of the idea is this is a little bit silly, but we can think about it this way. So in complex differential geometry, we have three key words, and they're the three words in the title. We have uh, it's complex, it's differential, and it's geometry. And so we didn't tackle them in order, but the first thing that we did is we added this part to our manifold. So think of it like our topological manifold is our base space, and now we're adding some structure on top of it. So the easiest thing to add first is the calculus structure. Okay, how can we do calculus on our manifold? So we did that, which gave us the smooth manifold. And so the next thing that we're going to tackle is the complex structure. So just like we had a CR differentiable structure, now we're going to talk about the complex structure. And this complex structure is going to be inherited by, our manifold is supposed to be, this is what we went over last time, is that it's Euclidean, locally Euclidean. But in the complex sense, this means that Euclidean means that it's homeomorphic to Cm and not Rn. Um, so, uh, in what sense is Cm a complex uh, vector space? That's what we're going to be talking about today. And there might be a definition of complex vector spaces that you might know already. We're going to look. This might not be the same one, and we're going to look at how those are the same. And once we establish this complex structure on this vector space, what does that like some of the interesting things that happens because of that structure. So this is what we're going to be looking at today, the complex structure. And then just teaser a little bit, we're eventually going to look at this structure as well. This is going to turn our manifold into something called a Riemannian manifold. And we're going to give it, I think it's called a metric structure. It's going to make it a metric space. Notice that the word metric and the word metry in geometry is like shared. So yeah, we're eventually going to get to that too. So we're going to like add all of it. So okay, complex structure. Right. Um yeah. So we already discussed that the locally Euclidean means were on Cm. So in order to define what a complex vector space is, complex vector space, we first need to define what a complex structure is. So, right. So let V be a vector space, a real vector space, if we have a linear map J that goes from V to V such that if we take the square, which really just means J after J, then this has to be equivalent to taking the negative of the identity map that exists from V to V. And uh, it's in this sense that J is supposed to be an analog to multiplying by I in the field of the complex numbers. So this is supposed to be uh, analogous to taking I square is equal to -1. But instead of having this algebra element that squares to -1, we lift that up to this idea of having maps. So what is the square of a map? The square of a map is you applying the map 2 times. And what is the analog of having the negative of the identity? Well, it's the negative identity map. So that's the sense in which we are calling this the complex structure. And just like how in the complex field, if we were to say promote the field of the real numbers to the complex numbers, one way we could think about that is that uh, well, introduce this algebra element called I and allow things to be multiplied by I. And so then what happens to that the algebra? How does it expand, and when can you close that algebra? Um, that kind of gives you the complex number. So it's kind of the same thing that we're doing over there, we're doing over here, except the way that J is going to work, we can draw an analogy with the complex numbers. So let's say that this is the complex plane. So and let's say that I have a vector on this complex plane, like an arrow. If I want to visualize what it means to multiply something by I, then we can see that it's a 90-degree rotation in the clockwise sense. So it'll take something, take my vector that is pointing, I should call it an arrow. Take my arrow that's pointing along the x-axis or the real axis, and it'll rotate it 90 degrees counterclockwise, and it'll give us an arrow that is pointing in along the imaginary axis. And you can keep doing this. You can see that if we take I and multiply by I 2 times, it's the same thing as taking the vector and rotating it 180 degrees. That's the sense in which I square is equal to -1. But if we take this to a vector space, what we want to say, and this is not going to be apparent yet. This is kind of like an intuition that I'm going to explain right now, and which we're going to understand more fully once we get to it. But if this is one of the vectors, it doesn't have to be a basis vector, but in this case we'll call it a basis vector. We might have two basis vectors in this space, and J in this situation will take us from one basis vector to the other. And then a repeated application of J will take us to the negative of the basis vector, minus E1. So that's kind of like, so you can see how we're trying to make this generalization from I to J. So this is the complex structure. So a complex vector space is, so complex vector space is a real vector space that admits a linear map J that uh, satisfies, oops, that satisfies J square is equal to minus identity. I'm writing it short here. So in other words, if a real vector space admits a complex structure J, then we can think of it as a complex vector space. Okay. So the next thing that we want to say is that this definition of a complex structure is exactly the same as the one that you may have already encountered, which is a complex vector. I'm not going to write out the whole thing. Let's just say a vector space. This should be, yeah, a vector space over the field C. And in a very loose sense, what you can think of that as is that when we do scalar multiplication, I mean, according to the definition of a vector space, there needs to be an addition and there needs to be a scalar multiplication, and there are about 8 axioms, as far as I remember, 8 axioms that the vector space needs to satisfy. Some of them are related to the scalar multiplication, and the field C, or the field of the vector space, is where you get the elements of that will scalar multiply. So if the scalar multiplication is defined using numbers from C, then what we end up is a complex vector space. So this is like before now, that's kind of the definition that complex vector spaces had. And actually, these two definitions are equivalent in the sense that if a vector space is complex in the sense that we just defined with a complex structure, it's also a vector space in this sense. So let's say that this is sense 2, and let's say that sense 1 is has complex structure J. So if a vector space is a complex vector space in the sense 1, then it's a complex vector space in the sense 2, and vice versa. So in that sense, they're equivalent. And we can show this. So I'm just going to outline this proof here, and I'm going to go over the main concepts of this proof. Even in the notes, I haven't written out the proof explicitly, completely. One of the reasons was time constraints. I was writing this yesterday, but it's also just in general, there's a lot of busy work that doesn't really reveal a lot about the proof. It's just that you have to verify all of the axioms, but the main idea is still there. So we can go from 1 to 2 by saying, so in order to prove that they're equivalent, we have to show that 1 implies 2 and that 2 implies 1. And the way we can do that, so the way we can go from 1 to 2 is, first of all, we say that V is a vector space, and we know that, and it has a complex structure, and we assume that it has a complex structure J. So then we know that J is a map such that J after J of V is equal to minus V, where V is an element of the vector space big V. If we can now define a scalar multiplication, let's say we take a random, an arbitrary complex number, a plus bi, and then we multiply it in the complex scalar multiplication sense with v, then that must be equal to a, and this scalar multiplication is in the real sense. We have this because v is a real vector space, multiplied by v, plus b real multiplied by j of v. So all we've done, we've taken this from the fact that v is a real vector space, and we've taken this from the fact that we have a complex structure on this vector space. And this allows this definition is completely compatible with the complex scalar multiplication. we can show that it satisfies all of these properties. I'm going to write out the properties, but we're not going to prove them. So C dot V plus W is equal to CV plus CW, C1 plus C2 into V is equal to C1V plus C2V. The next one is called compatibility with scalar multiplication. So C1 dot C2, so this should be an R into V. So this one will be complex. So then that's equal to C1 complex into C2V, where C2V is the vector that we get as a result of scalar multiplication. That kind of this property basically tells us that um, with applying one and then the other is still is possible. So it's like a well-definedness check. So the last one is that there needs to be some identity element over the scalar multiplication. 1 times V is equal to V, and we have to check that this works. A lot of these are, you might think that these are almost obvious, but like they're obvious because we can check them in our head. Right. So if all 4 of these uh, properties are satisfied, then we know that this is a well-defined notion of complex scalar multiplication, which means that we can treat V as a vector space over C. Because the addition, I mean, in a very subtle sense, you might want to check that the addition doesn't get messed up by the fact that we introduced this scalar multiplication. So if you really wanted to be thorough, you would check all of the axioms of the complex vector space. But um, overall, I mean, we can kind of we intuitively have a sense that the addition will not be messed around with. So mainly what we want to check is that the complex scalar multiplication works the way that we expect it to work. And so since that is satisfied, we know that V must be a vector space over C because it's a structural definition. As long as it obeys the axioms, it must be that structure. So we know that B is a vector space over C. So then we do it the other way around. What does it mean to do it the other way around? Well, first we say that, well, let W be over C, right? And then we have access to the complex scalar multiplication, but we don't have a complex structure J. So we say that, okay, let J be a linear map such that J of W is equal to IW. Remember, we have access to I from this direction because we're working in a vector space that includes the complex numbers or is over the complex numbers. So we're allowed to scalar multiply I into a vector where W is an element of big W. Um, and so we can verify that J square, which is equal to I times well, okay. What I meant to say is J square of W is equal to I times W, which is indeed minus W. So J is indeed and J is linear. You can check that too. So J of V plus W is equal to I times V plus W, but that's also equal to I into V plus I into W, which means that it's equal to J of V plus J of W, which means that J is a linear map, which means that J is indeed a complex structure. Remember, we just said that J was a map. We didn't we didn't know yet whether it was a complex structure. We defined what J did, and then we proved that it must be a complex structure. Okay, so that means that W has a complex structure. But also we need to show that W works as a real vector space. So the way we do that is that right now we have W uh, where, okay, let's call this W tilde because this is W. W tilde is the set of elements of vectors without the vector space structure, without the addition and the multiplication. So we have W tilde, we have the addition, and we have the complex scalar multiplication. So what if we restrict this and we say that, let's say that V is equal to the set W with the same sense of addition, but only real scalar multiplication. So you can think of this as a restriction on the original space. So we still have all of the elements. We're not getting rid of any of the complex elements. We're just getting rid of the complex scalar multiplication. We're not allowed to multiply by any number that has an imaginary component with it. So if we do this, then we can see that again, a plus bi dot w, this is the complex scalar multiplication that we have on w, is equal to a real scalar multiplication into v plus, sorry, this should be w, that's a typo. W plus b dot r scalar multiply, real scalar multiplied by j of v, where j of v comes from the fact that we're taking this I, we're distributing it into this w, we get iw, which is equal to j of w. From our previous definition, that j of w by definition is equal to iw. So we can see that any scalar multiplication can be rewritten in terms of this. This seems similar, but like from the way that we were doing it in the other direction. But we approached it from the other side, and we showed that it still works. So we find that W can be thought of. Well, by the way, so this is a real vector space, right? That's the idea. So W can be thought of as a real vector space with complex structure J. I think we have a notification here. I'm gonna. Okay, if there's a typo in my notes, I'll address that later on. You had a question about the dimensions? Okay.
I was wondering, like, the dimensions of V and W are not the same. Like, W must, like, they must have the same real dimensions, but like like W is an n-dimensional.
Yeah.
If W is an n-dimensional complex vector space, then V should be two n-dimensional. And I think maybe it's implicit, but you weren't very clear how you would go from a basis of W to a basis of V, because you can't just like I'm not sure, but I'm guessing you can't just like forget the complex part. I'm not sure if you'd talk about that at some point. I
Um,
don't. I'm not sure if you understand my question, but
no,
I
I got you. So we're not forgetting any of like we're not decomposing the vector elements, so that part's fine. So we just think of the elements of W tilde as elements of a real vector space, and we multiply them using the real scalar multiplication. Now that doesn't allow us to like just this is not enough to get back to W. That's the thing. In order to get back to W, we need the map J, which allows us to go from a real element to a complex element, which V doesn't understand what a real element and a complex element is. It just thinks of all of the elements as being just elements of a vector space. And you're right, the dimensions of the real vector space is twice the real dimension of the real vector space is twice the dimension of the complex vector space. But we didn't invoke that anywhere, and that doesn't ruin our proof. So we're actually going to look at that later in this notes. And um, you could say this proof is not complete without it, but if we didn't like kind of put it aside for a second about mm, the dimensions, we would have to go through all of the rest of the lecture in order to talk about uh, this proof. So I just kind of wanted to keep that point for another for later, and by the end of it, it will be clear how we decompose W into V. But yeah, it is a good concern. Right. So in fact, that's what I was going to talk about next, is that the one place where there's some cause for confusion is this place where what does it really mean for us to break down V, but we're going to work up to how we break down the vector basis into a complex vector basis into a real vector basis. Right. So now that we've established that both of the complex the definitions for a complex vector space are the same, now we're going to look at what this bringing in this complex structure J, what does it do for us? And in fact, unfortunately for your question, we probably will cut it into two parts. And so we will address the other part near the end of the second lecture on this on these notes. So, but let's start. So the first result that we have that's interesting is that we induce, so we have an induced complex structure on the dual space. And we can see that, right, so if we have a vector space V and we have its dual vector space V star, I'm going to actually remove the arrow. This kind of looks like a map. So if we have the dual vector space V star, then if we have J on that's defined on this real vector space V, then we can actually transfer this to, or we can define a complex structure on V star that from the information on J, which we're going to call this J star. In Chern-Chen and Lam, they call that one J as well. But because J goes from V to V and J star goes from V star to V star, I thought it would be less ambiguous to call the J on V star J star, and but it's the same sort of complex structure as J. So they're not two different types of complex structure. They're the same kind of complex structure. J star squared is also equal to minus identity on V star to V star. So what does the complex structure on V star look like? That's what we're going to look at next. So for this, we're going to look back at the inner product. We have V of J star alpha. So V is a vector. So V is an element of V, and alpha is an element of V star. And by definition, this is equal to J of V. This is how we're going to define it. We're going to say that we defined the basis and the dual basis by taking their inner product, if you remember from the lecture on tangent spaces and cotangent spaces. So similarly, we're going to define J star acting on alpha by considering its inner product with an element of V, and we're going to need these to agree with each other. We're going to need J star of alpha inner producted with V to be the same thing as alpha inner producted with J of V. So this implies that V of J star squared of alpha is equal to J square of V of alpha. And if that doesn't seem like it should be the case, first think that we're applying another J star on J star of alpha. And on this side, we're saying, well, then that's J of V, which is, we're doing the same thing twice. So that's why that counts. So, but we know that what J square of V is, right? Because we know that J is a complex structure on the vector space. So just like I, it will give us the negative. And then we use some linearity properties of the inner product. We pull this minus sign out of V, of the inner product. And then we pull it back into the other side. So since it's real, we don't have to worry about conjugation or something like that, which means that if we rewrite what we had on the other side, V of J star squared of alpha is equal to V of minus alpha. Since V is an arbitrary element of the vector space and it has to be true for all elements of the vector space, we deduce that it must be a property of the map itself. So J star squared of alpha is equal to minus alpha, which means that J star is a complex structure. So that means that if we have a complex structure J on V, that induces a complex structure J star on V star. Okay, so that's the first result. The second thing that we're going to look at is decomposing the eigenspace of J. Eigenspace of J. Okay, so I think this is a good time. I don't think we've talked about eigenvectors too much before, but amongst the topics in linear algebra, this is one of those topics that tends to cause the most confusion. So let me briefly discuss what eigenvectors and eigenspaces are. Let's say, like, coming back to our favorite thing to draw, R2. So if we have a linear map, right? In this case, J, but let's just say a random linear map. The linear map takes an input vector. Let's say we think about this input vector, call it I for input, and then it's going to take this vector to a different vector, call it O for output. So what A does is it transforms this vector to that vector, and it transforms every vector on this space into a different vector. So the eigenvectors of A are those vectors. Let's say we have one vector here in this direction. Let's call it E for eigenvector. Eigenvectors are the only vectors in this space where A has its only effect is to scale the vector up or down. by some factor in the um, in the field, right? In terms of if A is a real matrix, if A elements Aij are elements of R, then um, so here you have to have a basis, and then we'll get into all that stuff. When does A have matrix elements? But if it's a real, well, all or if the linear map is real, for example, we could say that if A is a real linear map. So then these will only be scaled in the same direction. When you have complex numbers, because I can rotate things, um, there it's a little bit more complicated what this means, but basically any vector or any vector on this line is going to get scaled up, right? Because if this vector gets scaled up, then let's say if we had a longer vector, then it would also get scaled up by a proportional amount. That proportional amount, it's usually denoted by lambda. It's called the eigenvalue. And it's like all of these are called eigen something, eigenvectors, eigenvalues. Um, Eigen is I think it's a German word that means characteristic. And the motivation for that is that um, uh, you can characterize a linear map A by its eigenvectors and its eigenvalues. And the eigenspace is the space of vectors. So let's say that I have one eigenvalue lambda, and let's say that there are two eigenvectors that have the same eigenvalue. So then I can form a two-dimensional subspace of my n-dimensional space using those two vectors as a basis, and that space is going to be called an eigenspace. So what we're going to do now is we're going to look at the eigenspace of J, and we're going, as it is a characteristic value, we're going to see if we can't characterize J using these eigenvectors. So that's what we're going to try to do now. But before we do that, we're going to need to actually figure out what J's eigenvectors are or eigenvalues are, and from there we talk about its eigenspace. Okay, so if before we get into this next part, let me just review my notes real quick. This next proof is gonna be a little dense. Where are we going to? Okay. So the claim is that the eigenvalues, oh, I'm still using blue. Eigenvalues of J are plus I and minus I, and they always come in pairs. This is the next result that we're going to prove. So let V be a vector space. I'm not going to write out all of that, with J being the complex structure. And let's say that this vector space has a basis. I named it curly B. Let me see if I can draw curly B here. Yeah, we're going to go with that for curly B. So this is the basis, the set EI where, or EJ as a type. Oh, right, I did write EJ. J is equal to 1 to M. Uh, this is a basis for V. And so we're going to be interested in the M times M matrix representation of J. And we're going to call this, so people don't usually do this, but I'm going to be very explicit about the notation here because I found it very confusing when I was reading through it. So I'm going to distinguish J, the linear map, and J, the matrix. So when I'm going to talk about the matrix, I'm going to put it in square brackets. And because the matrix elements depend on the basis, I'm going to put the basis here too. Because think if I do a coordinate transformation, this matrix is going to change. And so this I would suspect, or like I would assume intuitively that the symbol for that object would also change if its contents change. So and then the elements of this matrix were going to be called, so the elements, I'm going to call them J curly B KL, where K and L are two indices that go from 1 is less than, I'm going to say it like this, K and L are both between 1 and M. And that comes from the dimension of the vector space, which is, we're calling it M-dimensional, even though currently it's real. M-dimensional. Okay. The first thing to note is that since J squared is equal to the negative identity on V, that means that the square of the matrix representation will have to carry the analogous equation. J squared in the basis curly B is minus the identity matrix, the M by M identity matrix. Okay, but where after is the matrix representation of J and not J squared? So we're gonna see what it is in a moment. Um, but from here, we can deduce that the eigenvalues of J squared are minus plus minus I. So the way to do this without getting into concrete details is quite requires a few results from a lot of different places. So I'm just going to try to explain these results as best I can. Um, so firstly, we have uh, a matrix A is always, so this is fact number one, always diagonalizable. I'm going to get into in a little bit what this means. Let me just write this out. If it's minimal polynomial, this is another thing that we have to explain. Polynomial has no repeated roots. So this is a theorem whose proof I can't get into for like lack of scope on this whole um, lecture series, but this is true, and its proof is in Friedberg et al. You can find the link in the lecture notes. Um, and so we'll have to explain what this means. So I misspelled diagonalizable, which is not shocking at all. Okay, so a matrix is diagonalizable if there is a set of transformations that you can do on that matrix that makes it into a diagonal matrix. A diagonal matrix being one that looks like this, A11, A22, dot, 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 AMM, and these are all 0. So if there exists a transformation that will take you into this form, then a matrix is called diagonalizable. Um, having matrices be diagonalizable is very, very advantageous because you can see that if a matrix is in diagonal form, we can do math on it much more easily because most of their entries are 0, and multiplying matrices by each other becomes trivial. If I have another matrix, then we can just A11 times B11 plus A22 B22. It becomes much easier to reason about what the result of this matrix multiplication is going to be. Right? So if this was A and this was B, then AB in this basis would be this. So right. And so secondly, we need to look at what a minimal polynomial is. A minimal polynomial So a minimal polynomial is the smallest polynomial that in the matrix. So it's so let's say P is the minimal polynomial. It's the matrix J um, curly B. Uh, so it's a polynomial in this matrix, just like, you could have a polynomial in X that would be like something X squared plus something X plus, that's a quadratic polynomial in X. So this is a polynomial in the matrix that gives you 0. So for this case, that would be because we know this exists, right? So since this is true, this condition J squared is equal to -1, we know that the minimal polynomial is going to be this. That's the minimal polynomial. Think of this as like X squared. So that's the variable in this equation. So and since this is equal to 0, that's our minimal polynomial. Notice that this only has 2 roots and they're not repeated. So we know that J is going to be diagonalizable. The second thing that we need to do is, now that we know that our matrix is diagonalizable, we'd like to diagonalize it so that we can make an easier argument about what its eigenvalues actually are. Because especially like I talked about multiplication in the diagonal basis, but one thing that's extremely easy to do in the diagonal basis is to find something's matrices eigenvalues, because you can show this in linear algebra as well, that these entries turn out to be the eigenvalues. So so now we're going to pretend that we've taken JB into that diagonal basis. So I'm going to put a D there for diagonal basis. And this is the square that we're looking at. We take this thing's elements, then we know, because we know that the multiplication is simple like this, we know that this is equal to So that might be subtle. We exchange the indices with the square, but what does that mean? It means that this is the element of the square of the matrix. Well, the LK element of the square of the matrix. And this is the that would be the KL element. The KL element of the square of the matrix, and this is the KL element of the matrix. So this is a number. The thing that's in this whole bracket is a real number squared. And we know that because let's say that instead of B, we had A here again in the diagonal basis. you could see how if we replaced all of these, then each element would give us the square, right? Oh, right. We don't need to sum these. These are just the separate elements in the product. Okay. So this makes life easier for us because uh, we know that because of this, if we write this in index form, which I'm going to do on the next page, let's write that in index form. That gives us J in the D basis squared. Take the KLth element of that. That will be equal to minus delta KL. So again, we come to this symbol called the Kronecker delta. It gives us 0 if K and L are not equal, and it gives us 1 if K and L are equal. That's what we want. That's what gives us that diagonal matrix. So this is the negative identity expressed in terms of indices. So if we do this, then we can tell that if we take this square on the other side, we know that this is equal to the square of the matrix elements of the matrix. So we can rewrite it that way. J D K L squared is equal to minus delta KL. We couldn't have transferred the square over to the other side if we couldn't do this. So we take this to here, which gives us, so take the square to the other side. Then we get plus minus I delta KL. So that is, so along the diagonal, we have plus and minus I, which means that the eigenvalues of J are plus and minus I. So here, notice I'm going to write B because the eigenvalues are not changed when we move from one basis to the other. It's just that in the diagonal basis, it's easier to compute the eigenvalues. So this is what we were after. These are the eigenvalues of J. Oh, by the way, one thing that maybe I forgot to talk about, which might make it easier to understand why the eigenvalues might be along the diagonal, is that what does this look like if I write this again, A11, A22, AMM? Well, if you've done coordinate geometry in high school, then a lot of the times you saw a matrix that looked like that, and they would tell you, okay, take this vector, apply this matrix, and then write the result. And you would see that this is a matrix that scales this vector by twice its length, right? It'll become 2 times its size. So if, in fact, if we were to erase this and we instead put 3, then what we would do instead of making it twice the size, we would make it 2 times longer in this direction and 3 times longer in this direction. And we would end up with a vector that looked like that. So here, what's happening is that we're scaling by each of these factors. But what does it mean to scale a vector by a factor? Well, it means that it's an eigenvalue. And it's an eigenvalue only if, since we mixed and matched, it threw the vector off of this line that it originally was on, right? But what if the vector, what if that was our basis? What if this was the basis that we were working in? If this was the way that the basis actually looked like, then we would just be scaling a vector along a line, right? So in that case, so that would mean that each of these corresponds to one axis. So this is the this is for, you could say this is for the x-axis, or this is for the x1 axis. This one is for the x2 axis, and this is for the x3 xm axis. And each of these corresponds to an eigenvector. So in this basis, in the diagonal basis, this is also something that you can prove in linear algebra is that in the diagonal basis, all the basis vectors are eigenvectors. This is where the notion of diagonalizability, or like the question of diagonalizability, comes from. Because if a matrix doesn't have enough eigenvectors to create a basis, then a matrix will not be diagonalizable. So that's why we needed to check whether or not J was always diagonalizable before we made this argument. The last interesting thing that we wanted to prove is that the I and minus I come in pairs. And what I mean by that is if we were to draw the matrix, then what we're saying is that there would be like a plus I, then there would be a minus I, then there would be a plus I, there would be a minus I. The order actually doesn't matter. I'm just drawing it this way because it looks nice. But because you can, in a vector basis, you can shuffle the basis vectors, right? You could go to a new basis where x1 is x2 and x2 is x1. Um, so uh, so the order of these doesn't matter. The thing that matters is they come in come in pairs. So if for every plus I, you'll always have another minus I. Plus I, minus I. So how can we prove that this is the case? That this is what J looks like in the diagonal basis? Well, it's actually very clever, and Chern, Chen, and Lam don't get into it at all. And I don't know why. They say that the proof is obvious, but it took me a fair bit to understand why they were claiming this. So, in fact, if you were to take the characteristic equation again, the eigen equation, the characteristic equation, that's the equation where you have determinant of J uh, in the B basis minus minus lambda V, right? Minus lambda V is equal to 0. Did I get that right?
Yeah,
Yeah,
lambda I.
yeah, yeah, that's how it goes. I was trying to reshuffle the equation in my head. Right. So from
Need the
here you
V
get an
anymore, I guess. You just take the determinant of this. Uh,
oh right, yeah. Just take the determinant. Uh Yeah, what I mixed up two equations. Thanks, Ornab, for that. I mixed up two equations. So the first equation is supposed to look like this. Okay, so and then this is a vector, whereas this is not a vector. So let me explain. So this is the matrix multiplied by, in fact, let me write another equation above this that will make it clearer. J of B on acting on a vector V is equal to lambda into the vector V. This is what it means for a matrix to scale a vector. So from here, we can rearrange this. That will give us this, because we can always think of this as lambda multiplied by 1 acting on V. So then we can subtract one from the other since they're both matrices. And by the way, I'm not using a basis on the identity because it's the same in all bases. Um, so then you have right. So from here to here is an interesting jump. So what we say is this is a lot like when you did middle term break in high school, where we have two factors. This is factor one, and this is factor two. And what we did when we had that structure x minus alpha, x minus beta is equal to 0, we would say that either x minus alpha is equal to 0 or x minus beta is equal to 0. Why did we say that? Because if there two things are being multiplied with each other and they're equal to 0, then at least one of them has to be equal to 0. So what we're going to say here is that we don't want v to be equal to 0. That's not interesting. That's the solution where the vector that we're scaling is actually just the 0 vector. And then this is always true for that. No matter what you multiply with the 0 vector, it'll always give you 0. So the more interesting result is what happens if this is 0. Well, what does it mean for it to be 0? Well, actually, the um, the only time when this being quote unquote 0 will give you the 0 vector is when its determinant is equal to 0. So think of this whole subtraction as one matrix. Think of it as one matrix, and think of that matrix having a determinant which is 0. So this is called the characteristic equation. And now you can tell why it's called the characteristic equation, because it has something to do with eigenvectors. So solving for this will give us the eigenvectors. And one thing that's interesting about this, so this is where point number 3 comes in. Something that's interesting about this is a polynomial. It's a polynomial. If you write it out, if you like expand in terms of the elements, and it'll become a polynomial in lambda. And from here, you can solve for the eigenvalues, and then you can put that back into the matrix, and then you can find the eigenvectors. So we have a lot of interesting results on polynomials. And one of those interesting results is that if a polynomial is real, if a polynomial, by which I mean if it has real coefficients, has only real coefficients, then if it has any complex roots, if it has any complex roots, they must be, I'm going to erase this just for some space, complex conjugates. Let me say it must appear as complex conjugates, because what I mean is that if x plus iy, let me not use x and y, a plus ib is a root, then a minus ib also has to be a root. But we already know what the eigenvalues of j are. They're plus and minus I. So for every plus I, the complex conjugate is minus I. And for every minus I, the complex conjugate is plus I. Which means that for every root, there has to be its complex conjugate. So that means that it has to appear in pairs. The one last thing that I have to mention is that J is a real matrix. And since J is a real matrix, this polynomial is a real polynomial, which means that it satisfies the conditions for this theorem to be true. So therefore, the roots of this the roots of this polynomial will always be plus and minus I, and they will always come in pairs. And therefore, the eigenvalues of this matrix are always plus and minus I, and they always come in pairs. Okay, so we're going to, I think we've gone on for long enough today. So I'm going to wind down the explanations, and we're going to pick this back up next time. We're just going to go over these two corollaries. So corollary 1 is that since we have that the eigenvalues always come in pairs, and J is always diagonalizable. Say that 5 times fast. Always diagonalizable. That implies that the dimension of V is equal, if that's equal to M, then M must be equal to 2n, where n is an element of the natural numbers, not the integers. So that's another typo in the notes. Right. So we that means that V must be an even dimensional vector space for this to work. For J to be so what we said was that okay, well, J always is diagonalizable, and J's eigenvalues are always come in pairs, and this is true whenever J exists, which means that we can't attach a complex structure J onto a vector space unless it's an even dimensional space, which kind of makes sense. I mean, if you wanted a real vector space to turn into a complex vector space, you would need pairs of dimensions to pair up to produce copies of the complex plane. So for V to admit a complex structure, J, it must be even dimensional. My penmanship is faltering a little bit. Sorry for that. Um, Corollary 2 is that we can always form an eigenbasis. This is going to be very important in the next few theorems for V. So these are corollaries because they don't need any additional um, work in order to prove. They're just byproducts of what we've done so far. We're just highlighting them because they're important. Using the eigenvectors of J. So yeah. So eigenbasis, obviously with respect to a certain matrix, because if each matrix has its own eigenvectors, and if it has enough eigenvectors, you can make an eigenbasis based on that matrix. This eigenbasis will be a convenient tool for us to prove some of the theorems later on. Right. So that's it. So let's summarize what we've done so far. So first thing that we did was we defined a complex structure on a real vector space. We showed that this turns it into a complex vector space. We showed that this complex vector, this is the same kind of, I'm going to call it a CVS as um, a vector space over C. Then we started looking at some of the results on complex vector spaces and the complex structure. So I'm going to say that interesting results. One is we induced a complex structure J star on V star. And two, we showed that um, eigenvalues of J are plus minus I. Give myself some more space here. Oh, it's not going to be black, huh? And they always come in pairs. And from there, we got these two corollaries. I'm not going to write them again because they're already here. And we're going to use these in some more results. So next time, we're going to continue looking at um, the eigenspace of J, and we're going to see how we can use the eigenspaces of J to, well, we haven't actually found the eigenspaces. So next time, we're going to find the eigenspace or the eigenspaces. We're going to use it to decompose V star cross C. We need even more space now. Let me write it over here. And lastly, we're going to see how we can go from a real basis to and back from a complex basis, which is going to answer the thing that Arnav was talking about earlier. It's like how did we do that part? So this is going to require us to understand the eigenspace of J in order to not directly, but in order to bootstrap um, our understanding so that we can leverage that to prove this. So, right, that's it for today. So if anyone has any questions, this was from earlier, I suppose. I was thinking that perhaps there is a simpler way to do this without referring to matrix coefficients. Probably, but the diagonal basis is a way that works, and it's I was thinking about what is a simple way to um, what's something that could be explained um, because something might be conceptually simpler, but it could be much harder to learn about it. There's also time constraints, so like that was the first way that I uh, realized would work, so that might play into it as well.
Yeah, like if you don't mind me talking about it. So basically what I was thinking is just, sorry, just using the fact that you have an eigenvector. So let's say V is an eigenvector with eigenvalue lambda,
Yeah.
and JV is equals to lambda V.
Hmm.
Now you can use the equation that J must satisfy with it, which is J squared is equal to negative the identity.
Yeah.
From that you get a constraint on lambda. So lambda must satisfy the equation lambda squared plus 1 is equal to 0. So so to me that was the thing that first came into my mind. But like the
Hmm.
diagonal like basis argument also works. It's actually the same thing in disguise. But
Yeah.
yeah, but
Yeah,
yeah.
that's true. I think I went up to that first of all, but then I realized I'm gonna need to talk about it anyway because of proving that they come in pairs requires the uh well, I guess it doesn't require the basis, but it requires the characteristic equation and the theorem on conjugate pairs, the conjugate pair theorem. So yeah, I mean we couldn't avoid talking about matrices for that reason, at least the way I'm understanding it. Okay, anybody else have any questions? You can write in the chat or you can speak up. All right then. If nobody else has any questions, if you have questions and you're too shy to ask them, you can DM me on Discord and we can have a discussion on there too. All right. That's it for today. Thanks everybody for coming. And goodbye. I'm gonna stop the recording now.